Welcome once again to chemistry, or AP Chemistry at Huntington High School. I'm Brian Brown, and today we'll be looking at our third and final chapter to help prepare for our first test, and that deals with stoichiometry calculations with chemical formulas and equations. This chapter is going to be much more math intensive than what we've seen in the first two chapters. Now, one of the things that I talk about on most chapters, and really from this point on you're going to be seeing this, is one of the major components of this class is getting ready for the AP test. And on the AP test, there's always material related to stoichiometry. The test is divided into a multiple choice section and then 6 free response questions on the second part of the test. Well, on the multiple choice portion, 7 of the 75 questions, ballpark, deal with ideas from chapter 3. So this is heavily represented in the first 75 questions on the AP test. And then on the second portion of the test, the FRQ free response questions, almost every year there are questions related to stoichiometry and calculations with formulas and equations. So this is going to be an idea that is represented in both portions of the AP test heavily. Now, law of conservation of mass. We may lay it down as an incontestable axiom that in all operations of art and nature, nothing is created. An equal amount of matter exists both before and after the experiment. Upon this principle, the whole art of performing chemical experiments depends. And that was Anton Lavoisier back in 1789. So this is really one of the core parts of Dalton's atomic theory as well. So Dalton wasn't really the first or the only person to be looking at particle nature. He just was the first person to publish the overall Dalton's atomic theory. Now, chemical equations are concise representations of chemical reactions. So it's showing very precisely and concisely what kinds and how much of each substance is reacting in a chemical reaction. So in the case of CH4 plus 2O2, it means you have one CH4 molecule reacting with 2 oxygen molecules. And those are both O2 molecules. And you're going to make one CO2 molecule and 2 water molecules. You'll notice the number of carbons, hydrogens, and oxygens before and after exactly equals each other. So reactants are going to appear on the left side, products are going to appear on the right side of the equation, and the atomic amounts of both equal each other. Now, the states of the reactants and products are written in parentheses to the right of each compound. And in many cases, you'll see states, and in many cases, you won't. Quite often, when we're writing chemical reactions for each other, we don't include states. But however, in some situations, they're incredibly important, like when we get into thermochemistry, and we're dealing with changes of state and so forth. Those amounts become very, very important, or those states become very, very important. So there are certain situations where you must write them. But in many situations, we often omit the states involved. Now, coefficients are inserted to balance the equation. Remember, you can't change the formulas. All you can change is the amounts, and that's what the coefficient represents. Subscript tell the number of atoms in each element of the molecule. So the chemical symbol is H2O. That means one molecule of water is 2 hydrogen atoms and 1 oxygen atom, whereas in 2 H2Os, 2 molecules of water, we then have 4 hydrogens and 2 oxygens. Now, the coefficients really tell us the number of the molecules we're going to have. So, like I said, 2 H2Os, because we're doubling the amount, we double the number of atoms of each. Now, equations for the AP test. Now, we're going to get into this more later, but I wanted to introduce this for the first time. Question number 4 of the AP test is always, they give you a description of the reactants, and you have to write the balanced equation. So this is question 4 every year of the AP test. So writing reactions is something you will be doing. And predominantly in first semester, but a little in second semester, we're going to look at a bunch of different types of reactions. Those are the reactions you need to be able to handle. Now, on the AP test, all equations must be balanced. Now, that's balanced by mass and charge, something we'll be getting into more in the future that you really didn't worry about last year. Now, you don't have to include states for this particular question because it's typically not relevant, or even if it is relevant, they're not going to deduct points, so don't worry about adding in the states. Now, step 3, write the net-ionic equation. If you're coming from honors chemistry, this is something you did. If you're coming from regular chemistry, this is something we're going to end up having to work on a little bit. In a net-ionic equation, all substances that dissociate should be written as ions. So if you have any strong electrolytes, strong acids and bases, or ionic compounds, In a water solution, they're going to be broken apart into their component substances, which in the case of ionic compounds will be the ions. So you don't show them together NaCl. If it's NaCl in water, you show it as Na plus and Cl minus. So you disassociate anything that disassociates. All strong electrolytes break apart. And you leave out any molecule or ion that is not changed in the reaction. So if you have a molecule or an ion that's there at the beginning and at the end, you're going to cancel it out. Those are called spectator ions in the case of ions. So when you're writing the net ionic equation, you basically list all the substances in the form that it exists predominantly. So instead of aqueous NaCl, you write Na plus and Cl minus. And if you had Na plus on each side, you'd cancel out the Na plus altogether. So when you're writing the equations, you have to write it in the net ionic equation form, something we will be practicing more. And then finally, scoring, you always get 1 point for the correct reactants. So if all your reactants are right, you get 1 of the points. You get 2 points for your correct products. If there's only one product, you have to have the multiple things right about it. If there are 2 products, it's 1 point for each correct product. Next, 1 point for balanced equation. That's mass and charge. We'll be talking about that more later when we get into redox reactions in Chapter 4. And then 1 point for answering a question about the reaction. So they'll ask you some question related to the reaction. That's also worth a point. So it's a 5-point part or question for each part of question number 4. And there's always 3 parts. So this section is always worth 15 points on the AP test. Now, at this point, I'm just introducing the idea, but we're going to use these ideas and sometimes even grade things like this so you get used to it throughout the year. Now, some simple patterns of chemical reactivity are what we're looking at in 3.2. In other words, these are our reaction types from last year. These are how certain types of chemicals behave with each other, and if you know the pattern, you can use it to predict and write the balanced equation. These are basically exactly what we looked at last year, so this is going to be a review for both those of you who come from honors as well as regular chemistry. First, you have combination, or sometimes referred to as a synthesis reaction. In this type of reaction, 2 or more substances react to form a single product. So magnesium and oxygen are reacting to make magnesium oxide. 2 substances reacting to make 1 substance. That would be an example of a combination reaction. So here we have a variety of different combination reactions. The first 2 would be elemental combinations. They're probably the easiest to predict because all you do is put them together and make the substance. Typically when you're doing this, it's going to be an ionic compound, but in the case of ammonia, it's not. That just happens to be a common substance, one you'll learn to recognize. But in most other situations, you're talking about metals and nonmetals, you're going to be making an ionic compound, so you use their charges. Magnesium's a +2, oxygen's a -2, so crisscross reduce 1 to 1. But you can also have non-elemental combinations. In the last one, C3H6, you should remember this from last chapter. It's a hydrocarbon, and it's 3 carbons, meth, eth, prop. So this is propane reacting with bromine, diatomic bromine. And that is going to make a brominated propane. So, and we don't really get into the formula at this point. We'll get into talk more about formulas and names second when we get into organic compounds. But here we're just looking at not all combination reactions are elemental combinations. What's happening here is the Br is getting substituted onto that compound in specific places. Now, all uncombined elements will be combination reactions. This is the one to watch out for. If you have elemental substances, all you can do with your elemental substances is put them together to make a compound. That's the type of combination reaction you really need to be able to predict. There are a few other exceptions to that, but the non-elemental combinations, we'll be looking at those later. Now, in a decomposition reaction, you have one thing breaking apart into multiple things. So in many ways, it's the opposite of combination. So one thing, 2 or more things. An example of this would be calcium carbonate breaking apart into calcium oxide and CO2, so metal carbonate decomposition. And then we also have potassium chlorate decomposing into a metal chloride, which is in this case the metal was potassium, so potassium chloride and oxygen. And then in the last one we have this reaction that produces ammonia and nitrogen. Notice it's decomposing into elements. Once again, if you have a simple binary compound, You can break them apart into their elements. If you have elements, you can combine them to make a binary compound. So this is kind of the opposite of the type of combination, at least at this point, you should be able to do. Later, we'll get into the other types of decomposition, metal carbonates and metal chlorites and a few others, and how they decompose. But at this point, really, the type of decomposition you should be able to do here is the third and final one. In this particular case, you have a binary compound. It will break apart into its component elements. And all you're really doing here is asking yourself, is it Hahn-Finkelbrei or not? Nitrogen is, so it's N2. Sodium's not, so it's Na. And then you balance your equation. This reaction, by the way, is actually how your car safety airbags work. You end up with this rapid decomposition to make nitrogen gas, and that blows up the airbag. So that's actually a really important one for survival. Now, decomposition reactions then are really when you have a single reactant. Binary compounds, except for peroxides, they're going to always break apart into two elemental substances. So when you see a binary compound, a two-element compound, you should understand it's going to break apart into its elements. Now, there are a few others that you do need to be able to handle, and we're going to introduce those here. So metal carbonates, you should know they break apart into metal oxides and carbon dioxide. So CO2 is coming out of that carbonate, CO3, and you're going to be left with a metal oxide. Metal hydrogen carbonates, they basically do the same thing, but you also get water. And you that's actually written wrong here. In a metal carbonate reaction, so let me fix this. I didn't realize that this was listed in the notes wrong here. So I'm glad I happened to look up and catch that one. If you look, notice it's telling you a metal carbonate breaks apart into a metal carbonate. That makes absolutely no sense. If you have a metal carbonate and it's breaking apart, even if it's a metal hydrogen carbonate, you can't get the exact same thing. So really where the problem lies here is this is supposed to be a hydrogen carbonate. So we're going to put hydrogen carbonate there. So the metal hydrogen carbonate is going to break apart into a metal carbonate, CO2, and water. And then metal chlorates, they break apart into a metal chloride and oxygen. So we've got a number of different situations here besides the plain binary elemental one, and that makes this a little bit tricky. How do you know how to do these? It's really memorization and common sense. Take a look at what you have and see what it could become, but on some level you have to have at least a little bit of memorization here. Now, in most of the cases, what we're really doing is breaking apart into a metal with a nonmetal. So we're breaking apart into a binary substance. So you're going to break apart into metal oxides and metal chlorides and metal oxides in these cases. That's kind of the common sense part. And then you look at what's left. Well, you got hydrogen, that means you got to have water. If all you have left are oxygens, then that means oxygen's got to be coming off. And if you had things that contain CO3, it's going to break apart into CO2. And HCO3, it's going to break apart into CO2 and H2O. So a little bit of memorization and the rest common sense will help you with these. But these are the type of decomposition reactions you should be able to handle. Now, in terms of combination reactions, besides the simple elemental combination, just do these in reverse. If it's a metal chloride and oxygen, you know you're going to make a metal chlorate and so forth. So these really work in both directions. They remind you of the decompositions you should be able to handle. They also remind you of the combinations you should be able to handle if you reverse your products and reactants here. Now, combustion reactions, these are generally rapid reactions that produce energy. So typically you're going to see a flame, like in the case of combustion of methane. Now, they most often involve hydrocarbons or hydrocarbons with oxygen. So a lot of times we just call oxygenated hydrocarbons. There are lots of hydrocarbons and lots of oxygenated hydrocarbons. When you burn them in air, they're going to undergo combustion. Now, examples of combustion would be the methane reaction that's listed here. And since this is C3H8, what is that going to be? Well, C3H8, if you try and draw it with a structural formula, you'd see, oh, it all is single bonds. So this is actually going to be an alkane. So C3H8 would be what alkane? Meth, eth, prop. This would be propane and oxygen. And that's also going to make CO2 and H2O. And that's because complete combustion reactions of hydrocarbons and oxygenated hydrocarbons always produces CO2 and H2O, and unless it's described differently, then we're always going to use these are our two products. So when you have a hydrocarbon, or complete hydrocarbon combustion, I should say, you always get CO2 and H2O as your products, which makes it easy to predict them. So always assume that it's complete hydrocarbon combustion. So hydrocarbons and oxygenated hydrocarbons, they're always going to make CO2 and H2O. So write your reactants, write your products, because they always have to be CO2 and H2O, and then balance. So those are a few types of reactions you should be able to understand and predict. So we had combination, we had decomposition. Elemental forms of each are the most common situations, but there were a few others. We looked at a handful of other situations you should be able to handle. In one direction decomposing, the other direction combining. And then we also had combustion. And that brings us to some other ideas from this chapter. We're not done with our reactions, but we're done for now. A formula weight is the sum of the atomic weights of the atoms in a chemical formula. So the formula weight of calcium chloride, CaCl2, would be the sums of the calciums and the chlorides. Now, when you're pulling numbers off the periodic table, generally you just go to tenths, unless that's going to restrict significant digits and we end up with an answer that's going to have less sig figs than we're entitled to. But normally that's not the case. So the vast majority of time, except when you've got things like hydrogen and lithium, which are very small, if you went to tenths, you'd only get 2 sig figs, and your measurements are probably going to have more than 2, but there will be situations where you have 3 or 4 significant digits and you may have to go to more than 1 decimal place. But the vast majority of time in chemistry we can get by with just going to tenths for our molar masses. But there will be exceptions to that, because you don't want a number that doesn't have to limit significance, like a molar mass, to limit significance. So if you can be lazy, then be lazy. Go to tenths. If that's going to limit your significance, then go to hundredths or thousandths, whatever the problem requires. But in most cases, you can go to tenths. So calcium chloride, we would traditionally represent that as 111.1 atomic mass units. Now, round atomic mass units to tenths from the periodic table, but always make sure you have at least 3 sig figs, because most of your measurements are going to have 3. But there, like I said, there may be situations where you may need 4 sig figs, and that may mean you have to go to more significant digits than just the hundredths place. Or just the tenths place. So it really depends upon the problem. But with hydrogen, get used to using 1.01. Otherwise, you're going to be limited to 2 sig figs, and your measurements almost always have 3. So hydrogen and lithium, just go to hundredths. And if you have to go to more, go to more. But that applies to things like even like calcium chloride. Now, molecular weight is the sum of the atomic weights of atoms in a molecule. So it's just a specific type of what we looked at before. The general term is a formula weight. That would be the mass of whatever chemical formula we got. If the formula happens to be molecular, we can call it a molecular weight. So if we had a molecule like ethane, then we would call it the molecular weight. But it's also a formula weight. And notice in this case we went to tenths. Well, why didn't we go to hundredths for hydrogen when I just said you should? Well, it's going to round out if we went to tenths for carbon. So unless we got enough oxygens, it really wouldn't end up affecting our overall atomic mass. In this particular case, would it? Well, think it through. If we went with 1.01, that would give us 6.06, which would add up to 30.06, and we rounded to 10, we would get 30.1. So that's how you'll see typically me do this problem. Will it be wrong if you have 30.0? Well, remember, one of the things I talked about earlier was for sig figs, you always get plus or minus 1 to the last decimal place. So if I had 30.1 and you had 30.0, it's still going to be considered correct because you rounded to the right significant digit place and you're within plus or minus 1 of that value. Now, if you're dealing with an atom, technically we would call it a formula weight. If you're dealing with a molecule, the formula weight is called the molecular weight. I should say, for an atom, the formula weight is the atomic weight. If it's a molecule, it's a molecular weight. And if it's an ionic compound, it would be the weight of the formula unit. So formula weight really is called formula weight for an ionic compound typically. Usually don't call it formula unit weight. Collectively, all of these are different types of formula weights. Really, the distinction is kind of inconsequential. And another name for this that we use collectively, which is what I typically use and probably most of you use. We call it molar mass. All these are fundamentally all different kinds of molar mass. And it's not really an important distinction, but I just want you to be aware, if you see atomic weight, that's talking about the formula weight of an atom. If you see molecular weight, it's the formula weight of an atom. Collectively, formula weight and molar mass, all kind of the same thing. Now, percent composition, easy type of calculation, but it's one you need to be able to handle. Remember, on top, it's the number of atoms times the atomic weight of those atoms over the formula weight, or the molar mass of the entire compound, times 100. So you should be able to calculate the percent composition of a substance. So the percent of carbon in ethane, well, we've got 2 carbons, and carbon is 12.0, and we add up all the hydrogens and oxygens to ethane. Remember, it was 30.0. Technically 30.1, but 30.0 will be okay. We end up with 80.0%. Next section, Avogadro's number. So we're getting into Avogadro's number, which means dimensional analysis is coming back, because Avogadro's number is a number of particles in 1 mole of a substance. So you have 6.022 times 10 to the 23rd molecules of water in 1 mole of water. And that means we have an equality, which means we can set it up as a ratio in a dimensional analysis problem. So Avogadro's number in moles. Remember, Avogadro's number is 6.022 times 10 to the 23rd, and 1 mole of carbon-12 has a mass of 12.0 grams. So that would mean 1 mole of particles is 6.022 times 10 to the 23rd particles. And it would also mean, in this particular case, if you had a mole of carbon-12, it would have a mass of 12.0 grams for every 6.022 times 10 to the 23rd particles. By definition, a molar mass is the mass of a mole of a substance. So technically, formula weight is not the same as molar mass, because we're talking about molar mass, we're talking about in grams rather than atomic mass units, and we're talking about how much a mole of it would weigh. But we often use the same 2 things collectively because they're going to be the same number. So the molar mass of an element is the mass number of the element that we find in the periodic table. The formula weight is in atomic mass units and will be the same number numerically as molar mass. It's just going to be a different unit. We're talking about atomic mass unit when we're normally talking about formula weight, and we're talking about molar mass, we're going to get grams per mole. It's the mass of a mole. Now, moles provide a bridge between the molecular scale and the real world scale, because normally we weigh things in grams, and molar mass can be used to convert grams into moles. And then once we're in moles, we can get to the number of particles, like formula units or atoms or molecules of a substance. So really, mole is a bridge unit between what we would measure in the lab, a real world situation, and what we could figure out, what's happening on the particle level, which would be, there's no such thing as a formula unit or a molecular number balance. We weigh grams, and we can use moles to convert that into the number of particles. So really, mole is a bridge unit. Now, 1 mole of atoms, ions, or molecules contains an Avogadro's number of those particles. So 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions of each element in the compound. So if you had 242 grams of calcium nitrate and you wanted to find out how many oxygen atoms that would be, you need to understand, remember, a bridge unit between mass and what we can't measure but we can calculate types of particles is going to be moles. So what we first want to do here is get rid of grams, and we can change grams into moles using molar mass. The molar mass of calcium nitrate ends up being 164.1 when you add them all up. Now, once we know moles of calcium nitrate, we can bridge into the type of particle. Calcium nitrate is ionic, so it would be formula units. So we're using next Avogadro's number to bridge. Well, at this point, we're not really done, because it asks for how many oxygen atoms we have. And that's where that last statement comes in. If we know how many formula units of calcium nitrate, we know that 1 formula unit of calcium nitrate contains 6 oxygen atoms. The O3 doubled would be 6. So we can use that last idea. Basically, this is an equality derived from the actual formula to convert to oxygen atoms. So Avogadro's is going to get us to particles. And the particles might be atoms, but in this case, it's formula units. So if we want to get to atoms, we're not done. We have to go through one more step. So here we're using the formula as a conversion factor. And this is something that should look very, very familiar to calculations you did last year. Next idea, finding empirical formulas from experimental evidence. To find the empirical formula from mass data, so we have to be given experimental data here. Remember that formulas are ratios of moles. So fundamentally what we want to do is take the mass that we're given and use it to get to moles, and then use it to get to whole numbers. And to do that, and this is really where the twist comes in, and once again, this is something you should remember from last year from any level of pre-AP chemistry, is when you get 2 moles are going to be goofy numbers, you need to get them to whole numbers. So if you divide by the smallest and double, triple, or quadruple, or whatever, if you have to, you'll get to whole numbers. So you can calculate the empirical formula from percent composition information. So if somebody has taken a sample, broken it apart experimentally, and determined what the percent composition is, in other words, found the mass of the elements and compared that to the mass of the overall compound, you would get percent composition data. You can actually use that to get an empirical formula. The steps you go through, get to grams, get to moles, get to whole numbers. So the compound para-aminobenzoic acid. You may see this listed in a problem as PABA, so this is kind of a common substance in organic chemistry. We don't really see it all that much, but sometimes they would tell you what it is and then later refer to it again as PABA. So if you looked at a bottle of sunscreen, it probably doesn't say para-aminobenzoic acid. It's going to say PABA. So read most bottles of sunscreen and you'll see it contains PABA. Not all, because some people are sensitive to this. So it may say it's PABA free. That just means it doesn't contain this. So let's say that it says you've got PABA, and the percent composition of PABA is 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. What's the empirical formula then of PABA? We've got that information. We should be able to go through the conversions. Remember, first we want to get to mass. That would be a molar mass conversion problem. As far as significant digits, when you do this, in general, I say keep extra significant digits, because the more you've got, the more normal your numbers are going to look at the end. You can round to sig figs like is shown here, but you don't have to. I usually tend to keep extra sig figs because it makes it easier for me to recognize when I've got the quarter, half, or third, and you got a double or triple or whatever, or quadruple. So in this particular case, when you take the numbers and you divide by the smallest, because we have to maintain the ratio of numbers. So we found out the ratio of moles in the last problem, but they aren't whole numbers. Well, to get closer to whole numbers, you divide by the smallest. In this particular case, when you divide by the smallest, you'll notice you get numbers that are almost all essentially whole numbers. So it looks like it's a 7 to 7 to 1 to 2 formula. Sometimes at this point you may have a third or a half or even a quarter, and that's where you have to double, triple, or quadruple to get them all to whole numbers. So remember, sometimes you need to double, triple, or quadruple. When you see a quarter, a third, or a half, that means you have to double, triple, or quadruple. The quarter would represent quadruple, the third or 2/3, so 0.66. Another situation you got to recognize is essentially a multiple of a third. That's a triple situation. And then when you have a half, that's going to be a double situation. So PABA ends up being C7H7NO2. Now that's not necessarily the formula of the molecule. In this case, it ends up that because the formula, or the empirical formula, ends up being the molecular formula. But in all situations, that's not going to be the case. It just happened to work out in this case. So that would be the empirical formula of PABA. And since that's actually what the molecule counts out as, this is also the molecular formula in this case. Now, a new situation that you didn't run into last year. Sometimes you actually burn a sample and collect the gases that come off and use that to figure out how much carbon and hydrogen you've got inside there. This is something you did not do in any level of pre-AP chemistry, so this is totally new. You need to understand when you have data that comes from combustion analysis, what they're going to do is they're going to tell you how much CO2 and H2O was produced. And you need to recognize all of the carbon in the CO2 came from the carbon in the original sample. So we can use that to figure out the actual mass of the carbon, but it takes an extra step. Same thing with the water. All of the hydrogen in the water had to have come from an original sample. So we can use the mass of the water produced to find out the mass of the hydrogen that was our original sample. So carbon and hydrogen can be derived from these two numbers. And you can see an example of an analysis, a combustion analysis problem on page 97, question number 3.315. So make sure you look closely at that one. Now, the one thing you can't figure out from just your amount of water and your amount of carbon dioxide is your amount of oxygen, because both of those contain oxygen. So we have to actually find our amount of oxygen based upon what's left. We know the mass of the original sample, and if we know it only contained carbon, hydrogen, and oxygen, we'd use the carbon from the CO2 to figure out how much carbon we've got, the hydrogen from the water to figure out how much hydrogen we've got, add those two together and subtract it from the original sample. What's left had to be our oxygen. So oxygen is really determined from the difference of the carbon and the hydrogen and how much was in the original sample. So make sure you look closely in your book to see an example of that type of problem. Next, stoichiometry. Remember, stoichiometry involves using going from one substance in a chemical reaction to another substance in a chemical reaction. And the bridge between those things is our mole ratio, which comes from the balanced chemical equation. So to do stoichiometry, you always have to have a balanced chemical reaction. So if they're giving you the balanced equation, it's often a dead giveaway. You're going to be doing some type of stoichiometric calculation. So coefficients in a balanced equation give the ratio of moles of reactants and products. And in a balanced chemical equation, those relationships between the moles are etched in stone, so we can use that to bridge from an amount of one substance in moles to an amount of another substance in moles. So starting with the mass of the substance, you can use the ratio of the coefficients between substances A and B to calculate the mass of substance B formed. And the bridge between those would be really this step right here. And that is really where our mole ratio comes in. And if we're going from one substance to another, we need to use the mole ratio from the balanced equation to do that. So we always have to have the balanced equation. Now, this can work whether it's a product going to reactant or a product going to a product or reactant going to reactant or reactant going to product like you traditionally see. You can always go from one thing in a reaction, if you know how much of it you've got, to predict how much of that other substance you would make or you would need. So if we have 1 gram of C6H12O6, that's actually glucose, a very common carbohydrate or simple sugar. You should remember it from biology. We can calculate from the mass the number of moles. And once we know the moles of one substance, we can use mole ratios from the balanced equation to convert to moles of any other substance. And then from there, we could go back to grams for moles if we needed to. So really your goal here is to get to moles so you can go from one thing to another. And then if you need to, get out of moles. In the case of particles, you'd be using Avogadro's number, beginning or end. In the case of grams, you'd be using molar mass. But there's other mole relationships that we've looked at. A gas at STP, that's a standard molar volume, 22.4 liters per mole for any gas at STP conditions. That's another way we can get from one type of unit to moles. We can also potentially use densities. We can use volumes to get to grams, then grams to get to moles. So there's a lot of different ways we can look at stoichiometry that may be new compared to what we did last year. Last year we did typical calculations like this: mass to moles, moles to moles, moles to grams. We did a little bit with Avogadro's and molar volume and maybe the formula, so how many atoms of oxygen in the substance. So there are other things we did, but predominantly we did pretty much mass to mass type stuff. And really this is a 3-step dimensional analysis problem. Now I've shown it broken into steps so you could get the idea. What we're really doing is getting to moles of one thing so we can go to moles of another, and then getting out of moles. This particular part is the basis of all stoichiometry. That's where you're going from one substance to another using the mole ratio from the balanced equation. Now, limiting reactants would be an idea related to the concept of stoichiometry. In most situations in the real world, you never have the perfect amount of each substance, so one substance is going to be used up. Now, technically all stoichiometric predictions are kind of limiting reactant type situations because you're assuming you have exactly this of one substance and you have extra of anything else involved. So technically pretty much every situation is a limiting reactant situation, but when you are given the masses of each reactant, you don't really know at the beginning which one is going to limit how much you could make, so which is the important mass amount and which is the unimportant mass amount. So in limiting reactant problems, you really need to establish what controls the reaction. So reactions occur, you never have the perfect ratio of reactants needed to make the reaction. One reactant will be consumed entirely, and then the reaction is going to quit. Any other reactants are just going to be left over. They're called excess reactants. The reactant which controls everything by being used up is termed the limiting reactant. And when you have a limiting reactant problem, your job is to first always establish the limiting reactant, and then basically start with that for every subsequent math problem. You can make cookies until you run out of one of the ingredients to make cookies. It's the same idea with a chemical reaction. Last year you may have looked at this as making brownies or making a cake or something. But most of us use this kind of analogy when we're first talking about introducing the concept of limiting reactant, because the idea of the concepts and really the math is pretty much exactly the same. Once this runs out, it could be sugar, it could be flour, it could be whatever. So once that one special substance or ingredient runs out, then you're going to stop making cookies. So once the family runs out of sugar, they need to stop making cookies or you're going to get really nasty tasting sugar. So really, once you've run out of a key ingredient in a cooking type situation, technically you could still make nasty product, but it's not what you'd want to make. It's not true in a real chemical reaction. Then it totally stops because you don't have any alternates. So in this example, sugar would be the limiting reactant because it's going to limit how many cookies we can make. It's also going to limit how much of all the other ingredients we could use. Now, the limiting reactant is the reactant present in the smallest stoichiometric amount. That doesn't mean the smallest amount. It means the smallest amount that gets used at the rate it gets used. You may have more of one particular substance, but if it's being used faster, you may run out of it first. So you can't just look at the masses or moles present. You have to really look at the stoichiometric amount. So you have to take into account the balanced equation and the rate of consumption of the things. So in other words, it's the reactant that's going to run out first based upon how much you have and how fast it gets used. In this particular case, it's the hydrogen that's going to run out first. And you know that because when the reaction stops, you see extra oxygen over there. So you only had enough hydrogen to make 10 water molecules. We had extra oxygen. So hydrogen would be the limiting reactant, oxygen would be the excess reactant here. So O2 is your excess reactant. So here's a typical limiting reactant problem. You're given the mass of hydrogen and oxygen. You may look at it and say, well, hydrogen, there's less of it, so that's going to be the limiting reactant. But you can't go that fast because you also have to take into account the stoichiometric way in which they get used. And remember, it's not masses that are reacting, it's moles that are reacting. So you can't just look at it on a simple ratio. You have to actually go through and see which one is going to make less. So to find the limiting reactant for this reaction, the one that controls everything, we're going to predict how much water each one can make. And the one that makes less is going to be our limiting reactant. So 2.50 grams of hydrogen. First, use molar mass to get it to moles. Notice here I'm using hydrogen to extra significant digits because I don't want to limit significance. Then I use my mole ratio of hydrogen to water, and then I use my molar mass of water. From that much hydrogen, if I had enough oxygen, I could make 22.3 grams of water. Then you turn around and do the same thing for oxygen. If I use up all 3.4 grams of oxygen because I have enough hydrogen, how much water can I make? Well, in this particular case, notice your oxygen, even though it had a greater mass and even though it's used at a smaller rate because of the difference in molar mass between the two, you're going to run out of oxygen first. It makes less water. So oxygen is your limiting reactant. You can make 3.83 grams of water, and hydrogen is going to be your excess reactant. So these two predictions tell us limiting reactant, excess reactant, and how much water could be made. We just don't have enough hydrogen to make more than 3.83 grams of water. Now, how much hydrogen was left over? Remember, the limiting reactant controls everything, and we just said the limiting reactant was oxygen. So find out how much H2 was used up by the 3.40 grams of oxygen, because oxygen controls everything. And then subtract that amount used from the 2.50 grams that we started with of hydrogen. So it's really a two-part problem. First, predict that we used 0.429 grams of hydrogen in using up all of our oxygen. And then we're going to subtract that from how much hydrogen we started with. So we had 2.50, we spent 0.429. And to correct Then we're going to round to the hundredths place here. 2.07 grams of hydrogen will be left over. So that's a type of calculation you should be able to handle. Make sure you go through sample exercises 3.18 and 3.19 to see other examples of limiting reactant problems. It's one of the most important math ideas of the chapter because we apply it in so many different situations. Stoichiometry is huge in AP chemistry, and stoichiometry is often about limiting reactants. Now, next idea, theoretical yield. The theoretical yield is the max amount of product that can be made. In other words, it's the amount of product possible as calculated through stoichiometry. When you're doing one of these stoichiometry problems, you're calculating a theoretical amount. If you're predicting a product, we would call it a theoretical yield. When you actually do the reaction, you get a different situation. You get the actual yield. Side reactions can steal yield. So there may be more than one chemical reaction occurring, and if you're losing reactants inside reactions, your actual yield is going to be smaller than predicted. It may also be a reversible reaction, so some of your product goes back and make reactants. That's going to steal yield. So the actual yield is always going to be smaller than your theoretical yield. One finds the percent yield by comparing the actual amount obtained, so that's got to be experimental evidence, has to be given the problem or you have to do it, to what was theoretically possible, and that's where the stoichiometric prediction comes in. So you take the actual divided by the theoretical, multiply by 100, and that will give you the percent yield. In industry, high percent yields are really what you're looking for because you can make more product, and if you can make more product, you can make more money. Make sure you go through sample exercise 3.20 to get a closer look at an example of theoretical and percent yield problem. And that ends our chapter 3 notes. Make sure you go through and look at those sample exercises closely.